Okay, so
Yes. So let n be a natural number. Show that x bar n plus y bar n plus z bar n
mhm,
is a polynomial in the variables
is a polynomial in
alpha, beta, gamma, where uh, alpha is equal to x plus y plus z, beta is equal to xy plus yz plus zx, and gamma is equal to xyz. Yes, yes.
okay.
Oh, and it's a polynomial with integral coefficients.
Integral
So we have to
coefficient.
show that.
Yeah, okay.
Yes,
Basically, you have to write it in terms of these things, right?
yes,
To write
yes.
it in terms of. So how do you do it?
No, I don't know, sir, but of course, we need to have alpha to the power n somewhere.
Right.
And I was thinking induction or something, but I wasn't able to like get the
Hmm.
factorization or something.
Yes. You can try it because it is, yeah, this particular one is, you can even write a recurrence, isn't it? You
Yes, yes, sir.
can,
Even I was thinking the
so
same.
what is the recurrence? So let's just call it Pn. Okay. Let's call this Pn.
Yes.
Right. So if you want to write Pn in terms of Pn minus 1, Pn minus 2, Pn minus 3, then what will the coefficients be?
Okay.
Can you guess? They will be alpha, beta, gamma.
Oh,
With some
okay.
signs, that you can take care of. Okay. So try
Okay,
to,
okay.
yeah, then you can do. It's not difficult.
Right, right. Okay. Yes, sir.
And this basically comes directly because you see, because these you basically consider the
Oh,
a polynomial which has roots as x, y, and z, right?
ah,
And then
okay.
you multiply by x, yeah, and then you add the roots and so on. So suppose you take t cube minus alpha t square plus beta t minus gamma, right? This polynomial qt. Here you put t equal to x, y, z and add them, right?
Okay.
Then you see
Yes,
you
sir.
can write x cube plus y cube plus z cube in terms of the lower things, right? In terms of the squares. So if you put this equal to x,
Yes.
then you equal to 0. Similarly, you put y.
And then we add
Z,
them.
and you add. Exactly. And when you want n power, then you can adjust the power, right, by multiplying appropriately by whatever
Yes.
t to the
Yes.
power n minus all that.
Y-
You
Yes,
see
sir.
you can see it like this. You can see it other ways also, but yeah. But you can also basically prove this also. You should try this, which is a generalization of this. So you see, this is a special kind of polynomial. This polynomial in x, y, and z, this is a symmetric polynomial. meaning you change variables, you change any of the variables here, you permute any of the variables here, the polynomial does not change.
Okay,
Right?
yes, sir.
It doesn't change, right?
Yeah, yeah. Yes.
And you see, for any polynomial which is like that, you can write it in terms of these polynomials, these elementary polynomials. Okay. So the statement will be like
Okay.
this, that you consider n variables. Okay. Then given this n variables, how many polynomials, tell me, how many polynomials of this type will you have given n variables? So first would be like maybe, yeah. Let's write it in
So
terms of
we
alpha,
can.
huh? Summation
So I didn't
xi,
understand the question.
right?
Oh,
So
okay, okay, okay. Yeah, yeah. Got it, got it. So yeah,
right,
yeah. So we can choose how many terms. So we can like summation of single terms, then xy, then xyz. So
yes, exactly,
yes,
exactly.
those
And like
summations.
this,
Yes,
so there will be n
yes,
such things, right?
yes, sir.
So there are n
Right, right. Yes,
variables,
sir.
and for n variables there are n, and these are called elementary symmetric polynomials, because these are the basics. These are also symmetric, right? Yeah,
Yes, yes,
and
yes,
these
sir.
are elementary symmetric polynomials. And then the theorem is that given any polynomial which is symmetric, meaning that this thing is equal to, if you replace this 1 by any permutation,
Okay.
meaning that this just means that applying a permutation, sigma is a permutation, right? So sigma 1 to sigma n
Yes,
is
sir.
like just permuting the variables. It doesn't change the polynomial. If the polynomial is like this, for all sigma, means that for all permutations, all the n factorial permutations, right? If it doesn't affect the polynomial, then this polynomial is called symmetric polynomial. And then the theorem says that this p can be written, as a polynomial of these things,
Okay.
in terms of these things, right? Some alpha 1 cube, alpha 2 square, mix of those kind of things, which basically just means that p is equal to q of these things.
Okay. Sir, and can non-symmetric polynomials be written?
No,
Uh,
no, because any
okay.
polynomial that you write from these polynomials, that if you take
It'll
these,
be symmetric. So
it will be
sum of
symmetric.
symmetric.
Right. So it's the if and only if
Yes,
statement,
yes.
because you're summing symmetric polynomials, multiplying symmetric polynomials, they will remain symmetric, right? So
Yes,
it's
yes,
a if and
yes.
only if
Yes.
statement. It's a if and only if statement. Okay. So you try this. I'm not saying this will be easy to prove. Okay. But you should
Huh.
try for three
Yes, sir.
variables and try to see this, read this, see what you can do. It's interesting. Some other concepts like
Yes,
homogeneous
sir.
and so on may also come in the picture. But I will suggest you try to do it for
Yes.
three
Yes, sir.
variables. When you try to do it for three variables, you can actually use this case that you have done. You can think.
Okay.
Yeah.
Okay.
So
Yes, sir.
this is not a good question, I will say, because it directly follows from something. Anyways, yeah,
Yes.
in that sense, it directly follows from something. So if someone knows about it, then they can just. But yeah, I don't know. Yeah. Proving it is also not easy
Yeah.
in the exam.
Yes.
If someone can
So,
prove,
sir.
if someone can prove that kind of thing in the exam, then they can also do that question directly. Yeah. Anyways,
Right. Yes, sir.
okay. So what were you
Yes,
saying?
sir. So, do we do Ugb 6?
Yeah, anything,
ISI
anything.
only.
Yeah, yeah.
Yes, sir.
ISI, UGB questions, 2023, of course.
Yes, sir. So we have U1. So U sub 1
Okay.
is 1,
Okay.
and UN plus 1 is
Uh,
equal to UN plus 1 over UN.
okay.
No, so 1 over UN is separate
Ah, okay.
for all natural numbers n.
Hmm.
So we have to show that UN
Mhm.
is less than or equal to 3 root n by 2.
So this n by 2 is in the root.
So
So
your
the
voice is breaking. What
oh
did you say?
yeah, is the 2 also in the root?
No, no, sir. It's
Okay. Like this?
simply yes,
Okay.
yes, sir. So, sir, what I found was there
Hmm.
is no equality. So maybe we should be looking for a stricter inequality that we can prove. That's easier than this.
Okay. Right. Correct. That might be good. Right. So if that's a stricter inequality, then that will be easier to use. Correct. But you know that I think that UN is at least 2.
Yes, yes. AMG.
Right. So can we not use these two things? Is this
Okay.
then then I know that maybe stricter inequality might be better, but mm,
Hmm.
if we can show this, we are done, right? Because this will be
Yes.
less
So
than this by induction and by one.
yes, yes. So we have to show that 3 root n plus 1 is less than 3 root uh, n plus 1, like whole thing. Yes.
Correct. And this is obviously true. No, no, sorry.
Okay.
Not obviously true, but you tell me if it is true. Eventually, this is true
Root.
because root n plus 1 minus root n that goes to 1, right? No,
Yes,
where,
yes.
I mean, no, sorry, no, no. What where does it go to? Can you tell?
It
What does it
doesn't. So it
goes to 1, right? Yeah, doesn't go to 1. This
so
thing goes to
doesn't it
1,
go to
goes to 0.
okay.
Oh, right, right.
Yes, I think it goes to 0. Yes, sir.
Oh, yeah, yeah. That's what I meant. Okay, I meant that.
Okay.
Yeah. Okay. Yes, yes. Of course, it goes to 0. Yeah, it goes to 0. So then that's not good, right? Yeah,
Yes. So we have a problem there.
yeah. So that's not what I meant. Yeah. I said something wrong. No, so that does not work actually. Yeah, I meant the ratio goes to 1. The ratio goes
Yeah, ratio. Yes.
to 1. So certainly it's not like this. Uh, hmm. So the ratio goes to If I take a stricter, you would also, I mean, either if you're taking a stricter inequality, you would also need to carry some lower bound simultaneously. Okay, then you can do it. Is there any lower bound? Not
other
half.
than 2, I don't know.
Sorry, yeah, not 2. But other than 2, if you can give a good lower bound, like in terms of n, then that
In
should do
terms
it.
of n.
Right, then that should do it. Yeah, because you will need a lower bound, right, to give an upper bound for 1 by un. And that constant lower bound will never work. So you can think of that. Uh,
So is it root n maybe? I don't know.
the root n, is it always given? Right. So if un is bigger than root n, yeah, then what about un plus 1? un plus 1 will be bigger than root n plus 2 by 3 root n, right?
Yes, yes, sir.
Yes, right. Is this bigger than root n plus 1? We can check.
So how did you get 2 over 3 root n?
This is, so 1 by this, using this also. So
Oh,
1,
okay, 1 by, okay, yeah, yes.
that's all, right? Yes, this looks correct, right? More or less.
Yes,
This looks
yes, sir.
correct.
But so we need to show that root n is less than or equal to un.
Though that is what I'm doing. I'm trying to show that un plus 1 is bigger than root n plus 1.
Oh, okay,
Right, yeah.
okay.
So that I'm checking here. And let's see if that is correct. Finally, it, no. Finally, this calculation come down to
3 root n.
yes, 3 root n plus 1. And
Yes.
this is correct, of course.
So 3 root n, sir.
3 root
Shouldn't it
n?
be?
Okay, sorry. 3 root n. Okay. Yeah, then it's even better, right?
Yes, better for us, yes.
So then I think you have this lower bound is good, right? Provided you can
Right, yes.
use this to prove un plus 1 is less than, that also you need to check, right?
Yeah.
Because you need to
How, but
simultaneously.
like, how do
Sorry?
we go from there to there? I'm not.
So let's see. So you make this assumption. Okay. So you make this assumption.
So for some n, okay.
So is it true for, it's true for n equal to 1? It's
Yes, it's
true
true
for
for 1.
n equal to 2 also. Root 2.
Yes.
It's true, right? And now
Yes, it's true. 1.5.
using this, we are able to show this, right? But you need to also show
Yes.
this,
Yes, sir.
right? And that you can do. So un plus 1 is equal to un. Just use it in the other way. So un is less than, let's see if it's correct, right? And un is bigger than root n. So 1 by un is less than 1 by root. Correct?
Correct. Yes, sir.
Now you try to now see if it is, we need to show this. This is the main thing.
Yes.
Correct? So
Yes,
it's
sir.
better than earlier we were putting half there, so it is better than that.
Right, yeah. And this is in terms of n too, so.
Uh, check it.
So this seems to be true only.
True, right? Yeah.
Yes, sir.
Yes, right. root. So then you're done.
Yes.
That's it.
Okay.
This, so
Yes, sir.
basically,
Yes, sir.
this which you said, right? This lower bound is the correct.
So you need to find a lower bound to find an upper bound
Yes, because you see that's
because
why
of this 1 by root n,
because
1
of
by
the
un. Sorry.
1 by u1, right? The half failed,
Yeah,
right? And
yeah.
when the half fails, you realize that nothing, no constant will work there,
Yes, yes, sir.
right? Yeah. So even if you want to prove a
Right.
stronger inequality, which we did not here, okay, maybe better solution would be to prove a stronger. But the point is that this problem is about having a lower bound also simultaneously. That's what I realized.
Yes, sir.
And maybe you can also like kind of simplify this equation through subtracting this and whatnot, right? That kind of thing trick can also work actually. But I don't know. I don't.
Okay. Yes, sir. Yes, sir.
This is a good. We solved a good way, right?
Yes, yes, sir.
Okay. So should we leave it for today? I think or
Yes, sir. Yes, sir. 1 hour. Yes,
we,
sir.
we solved the quality problem. That's, yeah.
Yes, we solved 3, sir. So we solved CMI 1, and then we solved ISI, the symmetric polynomials, and this inequality.
That's right. It's okay.
Yes, sir.
You see how we are solving means you have to get the hunch of the question, right? That you have to sit back and analyze, right? Like you have to go back to the time when you're sitting in the exam and now when you're doing. Well, where is the difference, right? What's the like? Yeah, the way I'm thinking and you're thinking, and one has to think. That's the purpose of having the because we all have this memory, right? So we need to use it fruitfully to build good habits, right? To build the
Yes.
correct
Yes, sir.
sense. Yeah.
Yes, sir.
Yes. All right.
So the main difference is like here when I'm sitting, I don't have like a lot of pressure to get the answer. Like even if I don't get it, I can like,
Right.
but there it's a lot of
Yes.
pressure. So
Yes. And that will be there, I think, right? But it's an entrance exam. Meaning, yeah,
yes,
it's hard to not feel pressured. Because it's an entrance
yeah,
exam and a lot of things depend on it. So yeah, I
yes, sir.
understand. You have to and all the good things you have to do under pressure. Actually. Like
Correct. Yes,
when
sir.
we are writing exams, your college exams, after that, if you're giving presentations, there is some pressure always, I think. And
Yes,
it's good. It's good. I
correct.
mean, you
Yes,
have
sir.
to, if there is no pressure, we won't improve. The real improvement happens in the pressure.
Right. Yes, sir. Correct. Correct.
Yeah,
Yes,
our
sir.
performance may not be very good in that process. It may not be 100%, but real improvement also happens there. I'm not saying it doesn't happen without, but anyways,
Yes, sir.
keep solving. Maybe we will do one, we can
Yes,
have
sir.
maybe one more class Sunday or Saturday. I will let you know in the evening
Yes,
only.
yes. Yes.
Okay.
Evening is fine. Yes, sir.
Yeah, I will let you know before, but today it was like, yeah, I said it.
Yeah,
Okay.
I was free only, sir, since holidays and
You have holidays,
uh,
okay. Yeah.
yes,
So
yes, sir.
how much time do you get to study during the day to think about maths?
Oh, sir, I study for like, so I do 3 hours. I try to do 3 hours real analysis, 3 hours algebra. Like this is my breakup.
Okay.
So I'm following Artin for algebra
Oh, you started?
and Bartle and yeah, yes, sir, I
Very good.
started. And Bartle and Sherbert for analysis. So
Very good.
3 hours each.
Very
Or
good.
I
Very
try
good.
to do 3 hours, but yeah, so usually around 3 hours each subject.
That is very good. 3 hours is a lot of time. Okay.
Yes, sir.
Yeah, that's good. Stick to these two books. Okay. Even
Yes,
if
sir.
at some point you get a little bored, don't leave them. Okay.
Yes, yes,
Continue
yes,
with it,
sir.
and you will see eventually that you will come out very, very strong in these two.
Right.
Yeah. Because
So
mathematics,
before university starts, like I want to be done with like at least 50% of both these books so that
okay. Okay,
I,
good. That's a good plan, but yeah, if you can do it,
right.
wonderful. But
Yeah.
Artin is a little big.
Artin is,
It's
yes, yes,
yeah,
it's
it is very
big.
dense. It looks like okay, but yeah, you see, because but if you can do, why not? I mean, you
Yes,
can
sir.
do. I think. I mean, so you're doing matrices, right?
Yes, sir. And I
Right.
have time till August, so it starts August 1st, all the universities.
Yeah. So no, actually, you have enough time. Vector space, they are all just
Yes,
building up on those things. Try it.
Yes, sir.
Bartlett and Sherbet you should certainly be able to do easily because
Yes, sir.
yeah,
Yes, sir. Bartlett and Sherbet, yes, I'm able to like work through it like quicker
yeah,
than Artin, so
yes,
quite quick actually.
it's easier. But Artin also, if you
Yes,
can
sir.
make up your mind, then you can do it. Yeah.
Yes, yes, sir.
Okay. All right, then I'll
Okay.
let you know. Okay. Bye.
Yes, sir. Yes.
Bye. Good night.
Thank you, sir. Bye, sir.